Hi, I'm Pavel, and today I'll talk about a practical problem that many developers face when orchestrating workflows. It's time-consuming flows that fail late. Imagine a flow that takes 30 minutes or 2 hours to complete, and you only learn that it's going to fail after the fact it fails. The question is then, what if we can predict that the flow is going to fail after the first or second minute of its running? And can we do something about it? Like abort, reroute, or warn the developer, ideally with a reason why the flow failed. And this is what this talk is about. Using early science and signals inside Prefect to predict risk before the expensive work starts. Very quickly, Prefect is a workflow orchestrator, as I said previously, in which you can define a flow. It's a basic entity of Prefect, and it consists of tasks. Basically, task is a unit of work. And the cool features of Prefect are that it's allowing to schedule task that can implement retries, caching of flows, and you can see the execution of flows in the UI. And you can interact in the UI with these flows, expand and collapse. You can also see the parameters, logs, timings, and failures of the flows. And the reason Prefect matters for this project is that it sits at the perfect point of the system. So right at the start of the flow, Prefect already knows a lot about what's going to happen. It knows the parameters, the environment, and metadata. And after the first task or second task, we can cheaply compute the quality fingerprints of data and collect early runtime signals. So instead of waiting for the expensive stage to burn the compute, we can generate the score of the risk it's going to fail early in the system. And Prefect has mechanisms that allow us to take action on this score. So to keep things concrete, I'll define failure as an SLA breach, just for simplicity. And we're just going to explore this particular definition of failure. So the SLA is when the runtime exceeds a certain threshold. And that's a common operational pain. And we want a prediction of that event early in the system, ideally on the runtime, on the submit time. And if we can predict earlier, we can do not just alerting, but we can do other things like completely stop the run, or maybe request a better machine that suits these particular parameters, and we can then distribute the compute better. Or we can simply fail and tell the developer what exactly went wrong, and that allows us to develop in much quicker cycles. In this particular presentation, I'm going to talk about a financial setting, specifically portfolio risk computation, and the flow looks like this. So we generate a matrix of returns for the first step, then compute some statistics, and after that, there's a heavy step that needs to be predicted if it's going to fail or not. It's a covariant estimation and some other simulations. So we exploit the fact that useful signals exist early. At flow start, we already know some of the data, which are number of assets, number of days, simulations, and other metrics like data quality measuring. Also, we know the version of the code, which is going to impact how we use these parameters in our calculations. And after the first step is completed, we can compute metrics for returns and measure the time that it took to calculate the first step. So in the end, I have defined 11 fields to form the feature vector. And I don't use anything after the heavy step, so only this 11. Then, right after the first task, we can run inference to get the probability that our runtime of heavy step will breach the SLA. And we attach the score to the run, and we can log the top drivers for interpretability. So the top features that contribute to this prediction. And only after that we can proceed to the heavy. Now, we run an actual prefect flow end-to-end, and the first task generates correlated returns, injects the missing values and outliers, and computes chip statistics. Then the heavy task does the real CPU work. And this is where we can avoid wasting time. And the parameters are not just linearly contributing to the runtime. So it's just the synthetic setup to test how we can learn models to predict more closely to what is in production. Well, while this is synthetic, what the idea is to show how can this be applied to Prefect and to actual production system, which involve nonlinear workflow behavior. When it comes to model choice, CatBoost is a natural pick for this task because this is a classic tabular risk modeling. We have mixed numerical features plus some categorical features, such as code version. And CatBoost tends to be a strong pick here because it involves minimal pre-processing and it can learn nonlinear interactions between features naturally. So I benchmarked it against a list of other models with the exact data and feature set. So I use logistic regression, random forest, XGBoost, the histogram gradient boosting, and just to have a sanity check, I also include a rule in which we just cut the threshold on a particular feature. And for validation, I use Rollout metric. And for interpretation of predictions, I use SHAP to explain why individual columns contribute to the prediction and how can we signal that to developers. Basically, I have done some testing of the system and I have run the system 5,000 times to get the data. And I've created a data set in which the SLA is picked the way that we have balanced classes of failures and success events. And after training and testing on the holdout set, this is the leaderboard that you can see. So the CatBoost is the best model, and it scores around 0.87 on Rollout. And we see that other boosting models also score quite high scores. And also logistic regression is also scoring above 80% on Rollout. A risk score alone isn't enough in our case because in practice we want to tell developers why this particular run is going to fail. If we know this information, we can quickly understand if we are missing something in the either input data or in the code. So we can compute per run explanations. In this example, the model predicted about 95% risk score before the heavy task with the SHAP, and the explanation of particular features that contributed to this score are listed here. So in this case, the returns had more extreme spikes than normal, and that make covariance simulation less stable. And also a lot of values are missing and had to be filled during the first step, which also contributed to instability. And this explanation can immediately suggest developers' actions, as I talked previously. Okay, so this is the UI of Prefect, and as in dashboard it looks like that, and it shows latest runs. As you can see now, we have 13,000 runs because I used to train models and generate data for that. And if we go to deployments, we can see there are there are two deployments. One is for successful runs and one for failures. And the difference is between only parameters that are provided to the runs, but the underlying code is the same. So if you go to successful run, we can trigger a new run like that. And if we go inside, we should be able to monitor it. And at the moment it's pending, so it will start soon. If we click into parameters, we can see we have numerical parameters and the categorical one, such as version. We see that the model here is used, the model we use here is CatBoost model. And now we see that the run is completed. We have the generation return step and then the heavy computation. If we go to the logs, we can see the run logs, and the earlier risk predicted is very low, doesn't pass the threshold. That's why we didn't stop earlier. So let's go into the second deployment, which is the risk deployment. And here we can look at the parameters and see that there are different. And we also can trigger a new run and see what will happen in this case. We have said here that it will not fail on the model prediction by default, so it should just tell us the probability of reaching, and it will not stop. It will, as you can see, continue the calculations here, but the early risk prediction is very high. It's above the threshold, so ideally it should be stopped. And we can see the top drivers for our prediction. Basically, we can use that for interpretability and tell what to this prediction. Yeah. And that will run for maybe minutes or two. We can actually suspend it, or let's cancel it. And if we are going to set the parameter to actually stop when the prediction is above threshold, we can see that it's going to fail the run. Let's see. So we click into the new run. Okay, so this is the run that we have triggered. And as you can see, it has failed. And if we see the logs, we see that early risk predicted is high. It's above threshold. We see the top drivers for that risk. And we see that the model enabled prediction breached because of this threshold. That's why the run has failed. So yeah, this is how it works. So how do we actually take this from a synthetic demo to a production flow that can actually change over time? For that, we need to take into account that the code can change, and many regressions are actually conditional. The same inputs can be okay in the first version of the code, and in the second version of the code, they can fail. So we need information about the changes. And we can get that either from Git commits or from the Git itself. And we can use the diff AST. And for reference, there are such tools as conventional changelog or change distiller that looks into the AST. Also, we need to roll out safely. Start in shadow mode and roll out only like features similar to alerting, and only when it's safe we can trigger the gating actions. Finally, we need to monitor the drift of the system. We can log the predictions historically and the outcomes that we took of these predictions, and that gives us the loop to retrain and calibrate the thresholds. And we also should utilize the sliding window for retraining the model, because we want to get rid of outdated data points. And in real-world applications, that can actually also be used. Cut. And the pattern actually generalizes beyond this synthetic financial example. Actually, any long-running workflow where failures are costly can be used. For example, ETL jobs, large batch scoring, ML models training, or CI pipelines that fail after hours, and like scientific workflows that need a lot of compute and CPU time. And the action is broader than just aborting. Sometimes the best action is rerouting, We can send the runs that predict to fail on this particular machine to a different worker pool. We can reduce the workload and switch to, for example, good implementation that we know is going to work. And we can tell the engineers what specific features contributed to this decision. And also, SLA breaches is not just one particular example of predictions. Another very practical label is retry success probability. If a task fails, should we retry? Will it succeed? Or we are just likely to burn some more compute if it won't succeed? And we can predict the probability of retry success. The main takeaway is that if you can predict risk early, you can turn Prefect from just being a passive orchestrator into an active control loop. So we can save compute and time and make failures much easier to debug. That's the main idea. So yeah, thank you for your attention.